looks like we're live. So yeah, hello everyone and welcome to another Zozin session. How about that? Hello Butterbird, hello. So let's make a little bit of an announcement on Discord server for everyone that the stream has started. Right, so alright, Circle live on Twitch, and what we're doing today, we are, drumroll, we are solving Project Euler problems in Porth. How about that? Isn't that cool? I think that's pretty cool. So we've been developing our own programming language called Porth for quite some time. You can find the link to the language in the description if you're watching on YouTube. If you're watching live on Twitch, you can find this thing by the command project. Right, so, and I think the language is mature enough to try to do something with it. And one of the things I decided to do on one of the previous streams is that I'm going to go ahead and try to solve some of the Project Euler problems in that specific language. And if while solving the problems we'll encounter some features that are lacking in the language, we're going to implement them and then we're going to solve the problem. So solving the problem will help us to identify what kind of things we're missing in the language for that language to be useful. So that's basically the idea. Hello everyone, hello recursive chat, XND, Aman, Video Nomad, Bitstream, Algorithm Shooter, MM2PL, hello, welcome, really glad to see you all. So yeah, and for those who doesn't know, Project Euler is basically an archive of you know, something like competitive programming problems, or so it's basically more of a computer science math problems. And yeah, I already solved a couple of them, actually more than a couple, but I solved them in a different language. I don't remember which one I used. I think I used a combination of C and Haskell and stuff like that. So, but I'm gonna try to basically solve those problems again, but in Porth. So hello everyone who just joined. Nafli, hello. So does it sound good? Sounds Gucci? Sounds Tamaguchi? I've got a little bit of tea. It's going to be very interesting. So is our language even useful for anything, for at least some imaginary problems? Alrighty. So let's take a look. So where is our language? So here is our language. And just to remind people, our language is basically stack-based, or sometimes people call this language concatenative. Right, so essentially, if you want to sum up two numbers, right, if you want to sum up two numbers, you basically do it like this. You do 10, 20, and plus. Right, so it uses like a reversed Polish notation. And essentially what it does is that when you do a number, it pushes that number into some sort of like a data stack, then it pushes another number into the data stack, and then when it encounters plus operation, it pops these two elements from the stack, sums them up and pushes them back. Right, and after that you can print this entire thing. And this is a valid Porth program. Right, you can go ahead and use the compiler to compile this program into an executable. As you can see, it will generate an assembly code, and then it will compile that assembly code with NASM, and then it will link that generated object file into an actual executable. Right, so, and here is executable that sums up two numbers, 10 and 20. So as you can see, it's a native executable, ELF64 bits. And if you try to run it, it will print 30, as you can see. Yeah, it's 30. Can you do stuff like handling GET requests, something that can communicate between services written in different languages? I'm not sure. So you mean something like HTTP? So, well, you can implement HTTP in that language, but, well, it will take some time, but eventually we're going to do that. So it's going to be rather interesting. We're definitely going to implement something like actually useful, like maybe JSON parser or HTTP client and HTTP server, at least for HTTP 1.1, you know, stuff like that. We only have syscalls, but I mean, everything in your operating system uses syscalls, right? It's just like the matter of implementing all of these things in Porth, right? It's just a matter of like doing all of that work. Okay, so let's actually go ahead and try to solve one of the problems and see how it goes. So I'm gonna like I kind of low-key want to use the solutions to these problems as the tests for the language. You know, that would be kind of cool. Maybe I'm gonna actually start developing right in the source code of the language. So it's gonna be a folder Euler. How do you spell Euler? It's Euler. There we go. And we're gonna start with the first problem. Multiples of 3 or 5. So if we list all the natural numbers below 10 that are multiple of 3 or 5, we get 3, 5, 6, and 9. The sum of these multiples is 23. Find the sum of all multiples of 3 or 5 below 1000. Okay, that sounds actually pretty feasible to implement right now, so let's go ahead and do that. So problem 001 Porth. What I'm thinking, I'm gonna try to first implement the thing that does things below 10, right? So what's interesting is that since we only care about multiples of 3 or 5, we can start iterating things not from 1, but actually from 3, right? So if I do 3 and while dupe is below, right? It's supposed to be below less than 10, we're gonna do dupe print. So right now I'm just trying to print all of the numbers from 3 to 10. Right, that's what I'm doing. So, and I'm gonna go ahead and just try to compile the entire thing, problem 01, and I'm gonna right away run it. I think I did a little bit of fucky-wacky. There we go. And as you can see, it went into an infinite loop that doesn't allow me to even stop this entire thing. And the reason why it went into an infinite loop is because I never increment the counter within the loop. Right, so it's kind of a dangerous language. It's a pretty unsafe language. You can go into an infinite loop. Right, there we go. So here we have numbers from 3 to 9, which was relatively easy to actually generate. So the thing we need to now do is check if the number is multiple of 3 or 5. How can we do that? So we can duplicate this number on the stack and maybe take a mod of 3. Right, we're taking a mod of 3. And interestingly enough, we can just check if it's equal to 0. Right. So if we take a look at the stack, so we have 3, then we duplicated 3 on the stack. And then we put 3 in there and we found the mod. I would actually like to actually replace this with an index, right? So now we have this thing in here. And then we compared it with 0, right? We compared it with 0. But now I need to have a second condition that does the same thing but with 5. So I need to duplicate index yet again, right? But I cannot just do a dupe in here, right? I cannot just do a dupe because it will duplicate this value on the stack. I want to duplicate like this one. For this one I have an operation called over, right? What it does, it duplicates the element over the top, right? So this is what I'm gonna have in here. There we go. Over the top. Or another solution would be to actually duplicate. Well, I mean, it's a good solution, I think. I think it's a good solution. So in here, we're going to push 5 mod equal 0. And as you can see here, we're going to have two conditions in here. Mod 3, right? So here is a mod 3. Actually, it has to be 5, right? So we have these two sort of like booleans on top of the stack. And I think we need to actually combine them with OR, but we don't have a logical OR right now, which is kind of sus. We only have a bit OR. But since the logic operations produce 0 or 1 anyway, I think logical OR, actually bitwise OR, is totally fine in here. Right, I think bitwise OR is totally fine to combine these two conditions together. Right, so, and there we go, we have some sort of a condition. Right, and if that condition is true, right, we're going to print that number. Otherwise, we're not going to do anything. Right, there we go. So we implemented some sort of filter that filters out only those things that are divisible by 3 or by 5. Right, so, and this is basically a condition for if. Right, so this is how it looks like in concatenative languages when you write it like this. The iteration variable being implicit is weird. So it's not implicit, there is no iteration variable. That's what's funny. Right, I can show you how the loops even work. So first thing we're doing here, we push 3 onto the stack. Right, so we have 3 on the stack. The next thing, while doesn't do anything. While doesn't do anything at all, it exists for the compiler to know where to jump when it reaches the end. So when the compiler reaches the end, it just knows that it needs to jump in here. And that's it. While does literally nothing. So then we have a condition. And the condition duplicates the number on top of the stack, then pushes 10, like so, and then it checks whether this value is less than 10, right, like this. So as you can see, on top of the stack, after these 3 operations, we have a boolean true or false. And now the next operation do, it does something. What it does, it takes a condition on top of the stack, and if it's true, it just falls through and executes the rest of the operations, right? It just falls through and executes the rest of the operations. But it was false, it will jump straight after the end and finish the loop. So there is no implicit or explicit variables here at all. It's just two instructions, do, which always pop an element from the stack and checks if it's true or not, and end, which always jumps to the while. And while does nothing, it serves as a marker for the end to jump to and check this condition again. This is how it works. And the iteration variable, right, it's something that is always on top of the stack. Right, and that's why I have to increment that thing on top of the stack at the end of the iteration in here. So, yes. Alrighty, so let's take a look if now we only have the things that are multiple of 3 and 5. Let's go ahead and run it, and as you can see, we don't have a mod. And the reason is actually rather interesting, is that because mod is not a built-in intrinsic. It's not a built-in intrinsic, it's available in the standard library, right? So I recently made some changes to the language. std porth is not found. Oh, I know why it is not found. It is because the std is available in here, right? And it's not in the include paths, right? So what we need to do in here, I think we have to do something like std, and there we go. So now it kind of works, but it didn't really do anything for some reason. Okay, let me see. So it consumed both of these operations, and now I want you to print anything, but it really didn't do much. This is really strange. So let me comment out this entire thing. So this is dupe print, right? So this is dupe print. Dupe print works, but if I do dupe 3 mod 0 equals, yeah, I have to swap it. I first have to put a 0 and then compare it. Okay, so I found a mistake. We need to implement some sort of like a static type checking that actually like catches this kind of errors, right? This is, I think this should be feasible, but I don't want to introduce static typing until after I implemented, I re-implemented Porth in itself, right? Because if I introduce static typing, it will complicate the compiler, so I'll have to do more work to rewrite it in itself. So I don't want to do that. There we go. So now we only have things that are divisible by 3 or 5. 3 is divisible by 3, 5 is divisible by 5, 6 is divisible by 3, and 9 is divisible by 3. So, and all of them are below 10. So all of them are below 10. And what's interesting is that, as I already said, mod doesn't work by itself. You have to include standard library. And this is because we don't have neither division nor mod operation in the built-in set of words of the language. The thing that we have, the thing that we have an operation div mod, right? This is the built-in operation, and what it does, it essentially takes two numbers, right? And then it divides A by B and pushes that, and then it takes mod of this entire thing and pushes that. So essentially it pushes two things simultaneously. And if you want only division and only mod, you can use this macro that basically drop unnecessary information, like drop and swap and so on and so forth. Right, and the reason why I did that is because it's a little bit closer to how x86-64 works. If you know, the div instruction in x86-64, it actually performs division and remainder simultaneously, and it pushes the result of the division into rex and the result and the remainder into RDX, right? So it's simultaneously available in both of these things, and I decided if you want to be efficient and just do these things simultaneously, you have this thing, and then you have an opportunity to drop just whatever you don't care about. Right, so I decided to implement it like that, and that's why it's in standard library. We have a lot of things in the standard library, by the way. I have like a syscall wrappers. I also have syscall constants, right? If you want to call syscall directly, you can pretty much interact with Linux now, right? At least you have like a read, write, and exit, and you can probably open files. You can already open files, by the way. I haven't tried that yet, but theoretically you can try to open a file and read from file and maybe generate another file, which is precisely what compilers do. Right, compiler is a program that opens file, reads the file, opens another file, and generates the content of another file. That's precisely what it's doing. That's precisely all of the interaction with the operating system it usually needs. Right, and we already have that in the language, right? So you can already do that, which is kind of cool. So kawaii freaking desu. Now what we need to do in here, instead of printing those things, we need to actually accumulate them. The question is, where are we gonna be accumulating this entire stuff? This is a very good question. We can be accumulating it on the stack as well. Which is fine, I guess, and we can try to do that. Okay, so we're gonna push the accumulator in here, right, and at the end of this condition, we only have the index, right, we only have the index at the top, and the accumulator over the top. So what we need to do in here, I suppose we need to swap this entire thing, right, so because what we're gonna have in here is accumulator, index, we swap them around, and then what I probably want to do, I want to do over, which will duplicate index over here, and then I want to sum them up, so this will give me this thing, and I suppose I want to swap them back, making an accumulator like this, and after that I will just increment the index by 1. Okay, cool. So after that, I probably want to drop the index, and here we go. At the top of the stack, I'm going to have the accumulator that I just need to print. That's pretty much the entire solution. That's pretty much the entire solution. Alright, so let me try to run the entire thing and see if it's going to produce. It produced 23. Is that the correct solution? It is 23, look at that, actually. It is straight up 23. So the next thing we need to do, we need to actually solve it for 1000. So what we need to do in here, we just need to replace it with 1000, and we have 233168. 233168. There we go, we solved it. So yeah, so it's kind of, and it's not that big of a solution. Like if you look at the how much it takes in terms of code, that's the whole code, really. Not that much. Though granted, it's a very simple problem and a very simple solution, but it generates an assembly, so it's like a native program and shit. That's pretty cool. So maybe I'm gonna start actually, you know, doing things, maybe testing. what you can do in here, by the way, in the test suite, you can specify the folder, right? And specify in the folder Euler, right? And then I can say record or record, I don't know how to probably pronounce it. And what it does, it actually records the output, the expected output of the program, right? And it puts it into TXT file, right? And the next time you're gonna run the tests on that folder, it will actually assert that the generated program outputted the expected result, right? If you made any mistake in the program, right, so we replace 1000 with 10, the test will fail, and as you can see, it tells us that expected 233168, but it got 23, right? So you can already use it for testing if you want to, right? So which is very convenient. Yeah, let's do 1000. Alrighty, and so this is just examples, this is Euler, and let's go ahead and implement the second one, even Fibonacci numbers. Okay, each new term in the Fibonacci sequence is generated by adding the previous two terms. By starting with 1 and 2, the first 10 terms will be like this. By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, find the sum of even valued terms. Holy fucking shit. So that means first we have to do the Fibonacci sequence, then we have to filter out everything that is odd and sum it up. That's a lot of different things, and we'll see how our language is going to stack up with that. Alright, so this is going to be problem 02. Right, it's going to be Porth. And we're going to include std Porth. So the first two numbers, 1 and 2. Okay, so 1 and 2. 1 and 2. This is what we have on top of the stack. And I suppose we're gonna use the first value as an iterator, right? So I'm gonna do over, right? So this is over. This is over, and let's say that it has to be less than 100. So let's just like learn how to generate Fibonacci numbers. Let's learn how to generate them. Right, after that, what do we have? I suppose one way to generate the next Fibonacci number is to essentially swap them, right? That makes the second one with the first one. Then I'm gonna copy the one that is over this thing, and then I'm gonna sum it up, right? So I'm essentially summing it up, and here I have something like this. There we go. That should be, you know, sufficient enough. On top of that, we probably want to print them. So I'm going to do over, copy the over, and then print it. So that will generate Fibonacci numbers that are below 100. Hopefully, we'll see. So let me see. And I did forget to do something, which is kind of weird. So what did I forget to do? Oh yeah, yet again. So I need to get used to the postfix notation. Yeah, I need to get used to it. Alright, so here are Fibonacci numbers, like from 1 to 89. There we go. So, and what's funny is that there is like exactly 10 of them, right? So this is exactly 10 of them. And maybe I can already try to sum them up. But summing them up already becomes kind of difficult, right? Because that means I need to have an accumulator, right? So I already have like A and B, like the nth Fibonacci number and n plus 1th first, n plus first, how do you say that? So, and now I have to put accumulator like somewhere here, right? So, and for instance, if I want to copy that value, I don't have a like over like 2 or not, so it's kind of not convenient. It would be kind of better if the accumulator was located somewhere in the memory. You know what I'm talking about? It would be kind of cool if it was located somewhere in the memory, and we have an ability to work with the memory. We have a memory buffer, and you can do mem, and that pushes the pointer to the beginning of the memory buffer, right? To the beginning of the memory buffer, and then we have operations like comma and dot that actually read and write into the memory. But here's the problem. These two operations can only write 1 byte, right? They can only write 1 byte. But here we need an ability to actually read and write bigger numbers, right? Because we have an accumulator, and the sum of the even Fibonacci numbers below 4 million is probably going to exceed a byte. It's probably going to exceed 255. So we need an ability to actually, you know, say how many, like what kind of number we wanna read and write into the memory. So I had the following idea actually. So that I would implement some sort of a typing for the load and store operations. So yeah, the comma and dot are load and store operations. So for instance, by default they're going to be 1 byte, and then I could say, okay, so here is a memory, and then I say U64 and read. And what this thing does, it sort of like hints what kind of type you want to read. So in this case, I want to read U64. The same is going to be with like dot, which reads and whatnot. That will be kind of cool, right? And then we can have different types. So by default, it's U8, then maybe U16, U32, U64, and yeah. But here's the interesting thing. I could probably implement that myself. Because if I can read 1 byte, what I can do, I can read 8 bytes and then construct a 64-bit number out of it. You know? I mean, it's gonna be slow, right? It's going to be extremely slow because you're essentially like pulling out byte by byte and then just constructing it onto the stack. And but it's going to work without modifying the compiler. That's the cool thing about it. Right. And furthermore, we have the system of macros, so we can actually tuck this entire bullshit behind the macro. That would be interesting, actually. What do you guys think? So yeah, let's actually try to implement something. Like, let's implement a macro called load64, right? That basically pulls out 8 bytes from the current memory. Do you have more than 8-bit arithmetics? Yes. So essentially, each number on the stack is 64-bit number. And every time you pull out a byte, it's actually converted into 64-bit number. So it's like, it's loaded into the lower byte of 64-bit register. So you can actually do some shifting and whatnot, and you know, it's going to be feasible. All right, so let's imagine how you would use that. Load 64, you would do something like memory, and then you would do load 64. So that means on the top of the stack in here, we have the pointer to the memory. All right, we have a pointer to the memory. So what I want to do with that pointer, right, I want to probably duplicate it, right? So I'm duplicating it, so I have the memory in here. So that also means that I need to maintain an accumulator, right? Accumulator into which I'm going to be saving all of that. So maybe one of the things I want to do, I want to first push the 0, right, like this, and swap it around, because I want to keep the memory pointer at the top, right? Because I'm going to be using it. All right. So then we also need to consider what is the endianness, right? So we're on x86-64 machine, so it's going to be little endian, right? So little endian. So it's a little endian. So then we're going to duplicate this entire thing, right? This gives us the... Oh man, that's actually very interesting. So, well, let's just try to implement that. So we got that, and then I can read this entire thing. So that means I now have this thing. And now I need to add it to the accumulator, right? Somehow I need to add it to the accumulator, which means that I already fucked up, right? Which means I already fucked up because I cannot just add it to the accumulator. Okay, let's actually go back. Right, so we have a memory, and then I push 0, right? I push 0. So the next thing I need to do, I need to copy over memory, right? I'm copying it over in memory, and then I'm reading this entire thing, and now finally I can add it to the accumulator, right? So I do plus, and that adds this entire thing to the accumulator. Perfect. So I have to do that like the other way around, right? I had to do that the other way around. So and if I repeat this entire thing, right, it will keep adding this thing up. But what's interesting is that before I will add that 0, I think I have to shift the accumulator by 1 byte to the left, right? So I need to actually shift it by 1 byte to the left. So this is memory. So maybe it would make sense to actually shift it somewhere here. So 1 byte is 8 bits, so it's gonna be 8. Right, this adds 8. A shift left, right? So this is gonna be shift left. So let's actually name it accumulator, and there we go. So we have something like this, and we have shift left. Then I do over, right? Then I read this entire thing, and then I sum it up. Right, then I sum it up. There we go. So now we have at least something repeatable, right? Now we have at least something repeatable. So because now we can do that 8 times. Almost. We almost can do that 8 times, because after that, what we have to do, we have to swap this thing around, right? We have to swap this thing around and add 1 to it, 1 plus, right? 1 plus. This will add 1 to this entire thing, and then we're gonna swap it back, and only then we'll be able to repeat this entire thing, right? And only then we'll be able to repeat this entire thing. There we go. So this is the line that is probably repeatable. So let me see. 1, 2, 3, 4. 1, 2, 3, 4. Right. And there we go. So we probably constructed a 64-bit integer, but it's not correct, by the way. It is not correct at all. You know why? Because it's a little Indian, right? So essentially, the least significant bytes are located first. So it's going to be A0, A1, A2, A3, and so on and so forth. And how we constructing everything? We essentially take A0, then we shift it, and then we put A1, A2, and so on and so forth. So as you can see, the least significant byte becomes the most significant one. So this way it is completely incorrect. So we probably have to, you know what, we can actually do a very interesting thing. We can set the memory to the end of the number and do absolutely the same thing, but instead of adding 1 to the memory, we can subtract 1 from the memory. So, and essentially it's going to be pretty much the same thing, but instead of moving from left to right, we're going to be moving from right to left. So pretty straightforward. What do you guys think? So we can try to do something like that. Okay. So we have 1, 2, 3, 4, 5, 6, all right, 7. So we have 8 bytes, and the memory actually starts somewhere here. So how are we going to be doing all of that? So this is the memory. We can essentially add 8, but that means this pointer is going to point at the thing before, or after the number. So I think what we have to do here, we have to add 7, right? We have to add 7. And then add this byte, and then move backwards. Okay, so let's give it a try. So at the beginning we have memory. So the first thing we want to do, we actually want to add 7. So it's going to be 7, 7 plus, right? 7 plus, this is plus 7. After that, we're adding an accumulator, which is going to be 0, right? So I'm going to put it like this. And to confuse people around, we're going to put 7 plus 0, and people who don't know concatenative languages are going to wonder, what the fuck is 7 plus 0? I think this is beautiful in my opinion. All right, so then we put 8, and then we do shift left, or is it shift left? Oh yeah, it's a shift left. All right, there we go. So we do shift left. Then we copy in the memory over, right? We copy in the memory over, right? And we are reading the byte, right? So essentially reading that byte, and there we go, we have a red byte. Then we add this entire thing to the accumulator, right? So we add the entire thing to the accumulator. Then we swapping this thing around, right? Swapping it around, and one. And this is where we have to do minus, right, there we go, we do have to do -1, right, so this is -1, which will result in 6, and then we're swapping this entire thing back, right, then we're swapping this entire thing back, and there we go. So now we can replace this kind of stuff. And what's interesting is that the last swap 1 minus swap is really not needed. Right, because this swap is gonna basically put it below the number, and it's like really not needed. So I can probably do something like this, right? So I can just get rid of that. Fuck that. All right. But what's interesting is that we're gonna end with a memory pointer and the final accumulator, right? The memory pointer and the final accumulator. And we need to get rid of the memory pointer. So what I need to do in here is just swap, drop. Right, so this is the last thing I need to do. Like a swap the memory and just drop it. So, and this is gonna end up something like this. Right, and we're gonna end up with just a single accumulator, right? It's just a simple accumulator. And this is what you can do without modifying the compiler to just read 64-bit number. Isn't it a beautiful language? I think it's a pretty cool language. Does it make sense? Hopefully that makes sense. I don't know. So we need to give it a try. So right now, in the memory, I suppose we have nothing. All right. We can try to just do something like mem load 64 and just print what we have loaded. Not sure if it's a generally good idea. So it's kind of difficult to test this entire thing unless we implemented store 64, if you know what I'm talking about. I think we need to implement store 64, because in that case I could just at least iterate over some range of numbers and just sum them up just to see if it works or not. But yeah, but we can just try to just run this entire thing and see that. Oh, okay, so it exited abnormally. Cool. It exited abnormally. I'm really happy. So I suppose, oh, this is because dot is writing into the memory. We have to read, right, we have to read from the memory. Okay, so that makes a little bit more sense. There we go. So, and it actually like printed 0 in here. There we go. This is roughly what I expected, but since we have nothing in the memory, so I don't know, that's fine, I guess. We can write something into the memory, like 255 or maybe like 69, like into least significant byte, like 16 memory, 69 write. Zaki08 subscribed with Twitch Prime. Thank you so much for the subscription. And also Lori Master is gifting a sub to Entrodox. Thank you so much for gifting the sub and supporting the channel. Really appreciate it. Okay, we can write a 69 into the memory, right? And so if we load 64, it's also going to be 69, so it's not really testing anything. Right, as you can see, it is 69. Though we could probably... okay, so Lug subscribed with Twitch Prime. Thank you so much for 3 months of Twitch Prime subscription. Thank you. So, yeah. Thank you so much. So if we actually put this thing 1 byte to the right, right, so it's going to be a slightly different number. So this number has to be equal to 69 multiplied by 256, if I understand this stuff correctly. So we can already kind of test this thing. So 69 multiplied by 256, and there we go. So it's actually matching. Right, so it is actually loading 64-bit numbers correctly, more or less. We can actually try to test this thing. So if I put 69 into the 3rd byte, this is the value we should see being printed. So let's actually give it a try. So if I put a 2 in here, and then I'm gonna try to do this thing, and as you can see, it's 45, 21, 98. Okay, so this operation works correctly, more or less, right? So we can already load 64-bit numbers from the memory into the stack and do some sort of operations with it. So, but we need to be able to store 64-bit numbers. Right, so macro store. Again, I do realize that it's kind of slow, and it would be better if the load64 was a compiler intrinsic, right? But I just want to implement it for now and see how slow the program will be, and then I'm gonna make it in intrinsic and see how much of speed up we're gonna get by making this thing intrinsic. You know what I'm talking about? I think it's gonna be kind of interesting. All right, so here is the macro, and okay. So what do we have in here? 0, 1, 2, 3, 4, 5, 6, 7. Essentially here, so we're storing a value, right? We're storing a value. Oh, and since we have a value, we're actually, by shifting it around, we can iterate it from left to right. We don't have to iterate it from right to left. Okay, this is actually perfect. I really like that. Okay, so here we're gonna have the memory and then the value. Right, we have a memory and then the value. So memory and the value. So what I want to do in here is probably copy both of them. So I have an operation called toDupe, right? So this is a toDupe, and that copies 2 of these values, right? 2 of these values. Then I need to extract a byte, the first byte out of this entire thing. So the question is how I'm going to be doing all of that. Well, I can put 255, right? So this is going to be the current byte, and then I'm going to combine it with the AND operation. So this is going to be 255, and there we go. And after that, I suppose what I can do is just write that into the memory, and that will write this value in this specific place, right? So that eliminates that. So after that, I need to actually move value by 1 byte, right? So what I need to do here is 8, and shift right, right? So this is going to be shift right. Cool. But I also need to advance the memory pointer. So I need to swap the memory pointer, like so. This is going to be that. Then 1 plus, and there we go. So now we have this entire thing, and we can swap it back. Cool. And we're back to square one. We're essentially back to square one, and we can just repeat that 8 times. 1, 2, 3, 4. 1, 2, 3, 4. And again, so at the last one, we don't really need to do swap 1 plus 1 swap. But one of the things we'll probably need to do, we need to just get rid of both of the values, because store just stores both of them, and that's it. So we can just do something like drop, or I think we can do toDrop, right? I think it also works. Okay. So that's probably the entire thing, which is a little bit more like simple. It's a little bit easier to store values than read them. And to test this entire thing, let's actually do the following thing. We're gonna have memory 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And let's store that value in the memory. Then we're gonna load that value from the memory, and we're gonna try to print it. And if everything is correct, we're going to see the 1, 2, 3, 5, 5 printed on the screen, right? So essentially what we did in here, we stored that value into the memory, and then we read it back. And what's cool is that store 64 and load 64 will expand into sequence of these operations. So we have macro system. All right. So let me try to do this entire thing, and it exited abnormally. Nice. Very cool. I wonder why. Is it because I forgot yet again? Well, I mean, yeah, I'm supposed to actually put dot in here, but I'm not kind of sure. So let's try to do that one more time. So let's try to understand what the hell is going on. So we have the pointer and the value, right? Memory and the value. So I do 2 dupe, right? I duplicate both of them, then 255 and end, right? This is not how it has to be, and end. So this is what we've got. And then I do a dot, and dot is the store you store in a single byte, right? That's what essentially we're doing. We're storing a single byte, so that will consume the whole thing in here. I didn't see any problem with that. Oh yeah, I'm just, okay, thank you so much. Yeah, thank you. I see, I was just missing them. All right, so let me see, and there we go. So it is correct. So I just made a mistake, but not in the macros themselves. So that's pretty cool. So now we can actually store and load 64-bit operations in a very scuffed way, but that's fine, I guess. All right, so we can try to do the following thing. I'm gonna iterate over like 1 while dupe 100 less. Actually, let's actually make it equal, right? And essentially, by default, in the memory, we have all of these zeros, right? So by default, we have zeros. So what I'm going to do in here is I'm going to duplicate the index, then read this value from the memory. Hector HSC, thank you so much for 100 bits. Okay, so I'm loading this thing from the memory, right? I'm loading from the memory and add it to the index. And now I need to save it back. So let's do that slightly differently. I think I'm going to put a memory in here, and then I'm going to do store 64. Right, so as you can see in here, I'm loading the value. Well, yeah, it's not going to really work that well. Okay. So here's an index, right, I duplicate the index, this is going to be the index, then I push the memory, this is going to be the memory, then I load 64, that gives me this thing, then I add this entire stuff, right, so as you can see we just added it together, and unfortunately I still have to do this like memory, right, which pushes the memory, and now I need to swap this entire thing to put memory in here, right, I have to put it in here. Oh, I could do a slightly different thing. Okay, so this is actually perfect. I can do memory. Zombie Cho, thank you so much for 3 months of tier 1 subscription. Thank you. So cool indeed. Thank you so much. And welcome to our epic Porth Club. That's right. So we're solving Euler problems in our own language. At least we're trying, right? Okay, so I'm going to do memory, that will put a memory, and then to copy an index, right, to copy an index, I'm going to do over, which will give me the index. It gives me the index. Or maybe I can actually do 2 dupe, right, so that will give me that. Then I essentially load 64 and then add this entire thing together and finally store 64 and finally, okay, so this is actually pretty cool. All right, and then I can do 1 plus, and there we go. Cool. You see, so now we have just like a very compressed expression. So now I'm gonna do mem load 64, and I'm gonna just print this entire thing. So we're summing up numbers from 1 to 100. That's what we're doing. And yeah, this is a sum from 1 to 100. I know that for a fact because of the progressions, right? So yeah, the sum for 1 to 100 is 50-50. So as you can see, yeah. We have no ability to read and write 64-bit numbers from the memory, but that didn't stop us from implementing this thing ourselves. Right. So we're pulling out the bytes one by one from the memory and we're constructing it on the stack. And it works. It's probably slow as fuck, but I mean, it works. We can use that as an accumulator now. Okay, so, and this is how it looks like. Holy fucking shit. Alright, so we have load 64 and store 64. We can actually put that into the standard library, I don't know. So Yeah, let's actually go ahead and put that in the standard library. Why not? We have a full control over the compiler, so now this is a part of the standard library, and we'll be able to just use this entire thing. Okay, so what was the problem? Does anyone remember what was the problem? The problem was to actually sum up all of the even Fibonacci numbers below 4 million. Okay, that's cool. So here we actually iterating over the Fibonacci numbers below 100, right? So that's what we're doing in here. So if I try to run this entire thing, so here are all of the Fibonacci numbers in here. So let's try to now maintain an accumulator, right? So accumulator is going to be somewhere in the memory. You know what? We have an ability to actually alias memory to something like ACK, right? There we go. So now every time I do ACK, I actually push the pointer to the accumulator, not to the memory in general, right? So we can sort of abstract it out. So we need to take a look at the even numbers, right? So I do over, then I try to divide the number by 2. I'm dividing it by 2, and actually I need to do a mod, right? And if it's equal to 0, only then I want to do something about it, right? Over print. There we go. So now we're printing only the even ones. But we need to add them to the accumulator. So I do accumulator, load 64, add it to the number. Then, so this is the number that I have. I put accumulator yet again, swap it, and store it back. There we go. So that should be fine, if I understand correctly, right? So here we have A and B. I do A, so then accumulator, then I load it, then I add it to A, right? I add it to A. Then I do accumulator yet again, then I swap it, and then I store it back, and there we go. So that should be fine. So that allows me to essentially accumulate everything into the memory. And then if I do accumulator load 64 print, that will print the final sum of these things. And we have 44. Is it 44? Right, by starting, well, it doesn't really tell us the sum. Right, it doesn't really tell us the sum, but okay. So I suppose now the thing we need to do, we just need to replace 100 with 4 million, right? So it's going to be 1, 2, 3, 1, 2, 3. And hopefully this entire thing is going to produce the result, right? Because we're iterating over the Fibonacci numbers and we just accumulating them into the memory. So let's see if it's going to produce the expected result. Okay, 461, 37, 32. 461, 37, 32. Good Duke, thank you so much for 26 months.
Hello, Ulipka.
Hello. Thank you so much for tier 2. Holy fucking shit. Thank you so much and welcome to our epic Euler Club. There we go. So we implemented this thing without the ability to read and write 64-bit numbers into the memory. Just think about it. What the fuck am I doing with my life? Like, why? But yeah, we have an ability to do that without reading and writing 64-bit numbers because we do that byte by byte. Right. I mean, we can just implement that in the compiler itself, but I wonder how much time it takes for the simulation. Simulation is probably completely unbearable. Right, so if I just run problem 02, it's still fast. You know what's funny? This shit is still fast. It's incredibly fucking fast. That's how fast the computers are in 2021. It's not even in 2021 because this computer is 7 years old, right? So that's how computers were 7 years ago. You could do completely nonsense solution that just instead of using like bulk reading from the memory, it can read 64-bit numbers byte by byte, and it's still gonna be fucking fast. That's how much we screwed up software. That you can do this kind of shit and it's gonna be fast. Let's actually see. So if I try to interpret this entire thing, I think it's gonna be super slow. So let's actually do the simulation. So how much time? It's still really fast. Well, it's 100 milliseconds, but yeah. You could write this interpreter in Python and it would be still fast. Well, I mean, we have, I mean, it's already written in Python. I mean, you're probably joking, but I mean, it's already written in Python. Anyway, so we have a compiler that generates assembly, and we have an interpreter that is written in Python as well, right? So, and the assembly that it generates is absolutely fucking horrible. But yeah. I wonder how fast it would be if you interpreted Porth in Porth and simulated that. I think it would be faster. I'm pretty sure it would be faster. But I have nothing to back that up until I re-implemented Porth in Porth. But my prediction, my intuitive prediction is going to be that the interpreter of Porth in Porth is going to be faster than the interpreter of Porth in Python. But we'll get to that conversation again once we do self-hosting. So, all right, so this is precisely, by the way, why I wanted to do these Euler problems, because it lets us know what kind of things we're missing in our language. So we can clearly see the things that we're missing in our language. I already kind of knew that. I just wanted to have a confirmation that yes, we do miss an ability to read big numbers from memory. Okay, so let's actually add that to the test cases. So I'm going to do test pi f Euler record, right? So this is going to be a record, and then if I just run the test cases, everything seems to be okay, right? There we go. So we can also try to run that in on a CI in the future. Alrighty. So what's going to be the next problem? What's going to be the next problem? Largest prime factor. Oh my god. Oh. I mean, this problem is super easy to solve. I remember solving this problem like this. So, yeah. So for those who doesn't know, like in a core utils, you have a factor utility that takes a number and factorizes it, right? So every time you need to factorize a number, you just have this utility. I think it's part of the core utils. Yeah, it's literally part of the core utils of GNU. But we can implement the factorizer in the in Porth. Why not? So this one is going to be rather interesting because we need two indices, like two things, right? We need the number and we need the current factor. Both of the things we can try to maintain on the stack. So the question is, do we need the memory in this case? I think we do need the memory for the final result, right? We do need the memory for the final result. So let's go. So this is going to be problem 03 Porth. Problem 03 Porth. Include std Porth. So what we're going to be pushing in here, I'm going to push this number and I'm going to push the first factor. So the first factor is going to be 2. The question is in which order I want to keep them. I think it would be easier to actually keep the current factor as the first one and this one as the second one, because then I can do while dupe is greater than 1 and we're going to do do. Okay. Or maybe not. You can actually keep them in other order, and in that case dupe is going to become order, right? So I think it's a little bit better, because then in the body of the loop I can do to dupe, right? Which will essentially duplicate this entire thing, and then I can do a mod of this entire stuff, right? I can just do mod. Yeah, it's actually a little bit easier to do it like that. And then I can compare it to 0, right? I can compare it to 0. And if it is equal to 0, that means we're gonna have one thing, otherwise we're gonna have another thing. Right. Oh, by the way, it would be kind of cool if we had like a to-do word that basically crashes when it reaches the execution, and it's not that hard to implement. You can make it a macro that looks like this. And what you do is that you can print something like to do right, to std error, like so, and then exit with a non-zero exit code, and that will work. By the way, we do have syscalls. We have wrappers for syscalls in our language. So we do have exit. You want to see how exit is implemented? I can actually show you. It's not a built-in word, by the way. It is not a built-in word. It's located in the standard library. And it's implemented like so. Macro exit. So it's a syscall of sysexit. Like we literally call it as a syscall. Because we have a syscall instruction, we can pretty much use the whole API of Linux. Whatever you can do in Linux, you can do in Porth. Right, so this is actually pretty cool. This is actually pretty cool, so you can have a to-do. And it would be also kind of cool if it put the location in here, but I'm not sure if it's implementable right now. So if I try to do something like this, 03, no such, one more time. Oh, yeah, we have to do compilation. Yeah, there we go. So it just says to do, right? It just says to do, but it doesn't tell you where exactly it failed. But anyway, okay. So what do we want to do in here? In here, I want to actually divide this thing by 2. If mod is equal to 0, right, I'll need to well, I probably need to swap this entire thing, okay, and then do over, like so, and then properly divide this entire thing, like so, right, and swap it back, and yeah, that's pretty much it. Which brings us brings us to another question. Maybe I should keep them in a different order, but whatever. So if it's not divisible by this value, what we can do is just increment that value by 1, right? So we can just increment that value by 1. So, and that's pretty much it. Do we need to do anything else? Every time we wanna print this entire thing, I can do dupe print, right? So, and let's take a look at all of the factors in here. Okay, so it exited abnormally. Where did I make a mistake? Okay, so this is going to be something like this. Over greater than 1. Okay, that's fine. Then we do duplicate of this thing. Then we do mod 0 equal. Right, and if it is true, right, we duplicate 2 and print it. Then we swap this entire thing. Right, we swap this entire thing. Copy 2, divide this thing by 2, and swap it back. Right, and swap it back. Swap it back. If it's not divisible, we always add 1 to the index. So the question is why this thing wouldn't work, or why would it actually, you know, fail? So I probably missed something. So, and also I think I'm actually getting tired. So, oh wait, oh well, it's a to-do. Well, I mean, probably not. All right, so maybe the time has come to make a small break, because I want to refill my cup of water and also, you know, yeah, to reset my brain a little bit. Because I've been doing a quite intensive shit for the past hour, so I think we do need a small break. So, Alright, so the chat actually told me that I made a oopsie-doopsie in here, so yet again, I still cannot get used to, you know, prefix notation. I think these kind of errors with confusing the order of operation could be easily avoided if we had static typing, similar to WASM verification step. And at the beginning, I didn't really want to implement the static typing before I made the compiler self-hosted. But I'm starting to feel that having some simple static typing might be beneficial in the long run while re-implementing the compiler in itself. So I'll think maybe we're gonna implement simple static like checking before doing self-hosting. We'll see, because that may help in the future. Alright, so let's actually see if it will print the stuff. And there we go. So here are all of the prime factors, right? And as you can see, yeah, we can even check that that's the correct prime factors, right? So if you do factor, these are the same prime factor. So, and essentially what we need to do in here is just, I suppose, print the last value, right? So I might as well just not print anything in here and print at the top. And yeah, there we go. So that's the solution. We didn't even need any memory access, so you just print whatever you have on top, because on the top we maintain the factor, the current factor. So, yep, pretty straightforward. So here's another solution. It's actually very simple. I really like how small and simple it is. Look at that. So let's see if we can add this entire stuff to the test cases. So let's actually record. So the simulation is kind of slow, but that's fine, I suppose. That's fine. Okay, that's cool. So the problem number 4, and I never solved the problem number 4. Fuck. Oh shit. Well, I don't remember how I solved these problems as well, so it's not that different from solving these ones. So let's actually go ahead and see. A palindromic number reads the same both ways. The largest palindrome made from the product of two digit numbers is 9009. So it's 9199. Find the largest palindrome made from the product of 3-digit numbers. So essentially, we just need to organize the nested loop, the two-dimensional nested loop, and we need to have a way to check whether a particular number is a palindrome or not. So that's what we need to do. Okay, sounds pretty straightforward. I have no idea why I didn't solve this problem before. So let's go ahead and give it a try. So maybe it should be easy. Okay, so Euler, problem 04, Porth, include. This is fun, actually. I really like that. So let's actually try to solve that for 2-digit numbers. So all of the 2-digit numbers are from 10 to 99, right? So this is what we can do in here. So while this thing is duplicate 100 less, we're gonna do that, all right? And then we're gonna do 1 plus, and then another one is going to be while duplicate 100 less and 1 plus. And you should not forget to actually drop the counter after the loop, and maybe we're gonna actually put the drop here as well. Okay, so here at the top of the stack we have 2 indices, right? What we can do in here, maybe we can just multiply them together, right? So here we go, we multiply them. And now we need to check whether this number is a palindrome or not. So the question is how we're going to be checking that. For now, we're going to just print this entire thing and see what's going to happen. So let me just go ahead and do this thing. And here are all of the numbers, right? So we're doing like a 2-dimensional loop, and we're multiplying the indices in a pretty straightforward way. Okay. So the question is, how can we check that a particular number that we have on top of the stack is a palindrome? Well, We can actually iterate through its digits and add them to a different number. So essentially you have two operations on a number: divide by 10 and mod by 10. If you do mod by 10, you essentially popping out a digit from the right. Right, so essentially you can pop out digits from one number and push them into another number. Then you can compare the results of those numbers. Right, so I can kind of simulate the process. Right, I have a number 1, 2, 3, 4, 5. Right, and then I have the second number, which is 0. So I add mod 10 of A to B. That means I will add 5. And then I can divide this thing by 10. Then I can multiply this thing by 10, which is going to be 50. And then add A mod 10. And 1, 2, 3, mod 10 is going to be 4. And this one is going to be 54. And then I can divide this entire thing by 10, 1, 2, 3. Again, I can multiply this thing by 10, multiply by 10, it will become 504. Then I can add a mod 10, which will be 3, right, which will be 3. And then I divide it by 10. And I can continue this process until this entire thing becomes essentially 0. And then I can compare the final result with the initial result. So this is how we can do that, right? So just like divide, mod, and that basically reverses the digits of the number. Does it make sense? Alrighty, so this is what we can do in here. RDB42, thank you so much for 7 months of tier 3. Hello. Thank you so much for 7 months of tier 3 subscription. Holy shit, thank you. And welcome to our epic Porth Club. Alright, so let me see. So, but we also need to preserve the original value too. So it's gonna be kind of difficult to do. So, alright, what I can do is I can duplicate A, right? I'm duplicating A, and I'm also pushing 0. So here I have these two numbers, so I need to move the digits of that number into that one, right? Somehow. We'll see how we can do that. But maybe I can do something like this, where I push first 0 and then I do over, right? Like this. And that will enable me all right. Okay, so let's actually do dupe. So this is going to be dupe 0, right? So this is going to be like this. Then I do over, right? This is over A. After that, I need to push 10 and do a mod. I can actually use percent, why not? So I have a percent in here. After that, I need to add this entire thing to this stuff. But maybe I need to back it off a little bit, right? So let's actually back it off a little bit. Because the first thing I probably want to do with the second number is to multiply it by 10, right? So I want to do 10 multiply, so this is going to be B, multiply by 10. There we go. So we multiplied it by 10. Then I do over, which gives me A, and then I do 10, and then I do mod. That gives me mod 10. There we go. And then I can do plus, right? I'm doing plus, and that sums up these two things. So we have this stuff. After that, I can do swap, that gives me that, and I want to divide A by 10, right, so it's going to be divide by 10, and then I want to swap this entire thing back, right, I want to swap this entire thing back, like so. And I kind of want to keep repeating this entire stuff until A becomes 0. So Hyaksu0, I hope I pronounced your nickname correctly, I don't know how to pronounce it. Thank you so much for 6 months of tier 1 subscription. Thank you, and welcome to our epic Euler Club. Which problem? It's a fourth one, so this is the fourth problem, largest palindrome product. Okay, so, and yet again, we need to keep repeating this entire thing. Need to keep repeating until a becomes essentially 0. Right, so one thing I can do over so this is going to be like this, while over greater than 0, 0 greater, we do this stuff. We do this stuff, and then this is going to be the end. And at the end, we have essentially 0 and final b. So, and I want to swap this entire stuff, so it's going to be b0, and then I'm going to drop the last 0. So, and if the number is a palindrome, a and b have to be equal, right? So that means if this is, well, I probably have to do something like equal if they're equal, that means I need to print that value. We can just go ahead and, I suppose, print it. Though, might as well do something like to dupe, right? To dupe and then compare this entire stuff, and then dupe print and then we can do to drop. Hopefully I didn't make too many mistakes. Okay, so this is the procedure that checks whether a particular number is a palindrome or not. It's kind of an involved procedure, but it is what it is, and it isn't what it isn't. We can go over it yet again. Why not? So it's actually pretty small, so I think shouldn't be that hard. So we have, after these two dupe, we have a. I duplicate a and I push 0, so we're gonna say that 0 is a b. Right, then I copy a over and then 0, and I check that while a is greater than 0, we keep repeating this entire thing. Then I do 10 and I multiply b by 10. Then I copy a over and I do 10 mod, so this is going to be mod 10, and then I sum them up, right? So I sum them up. Then I swap this stuff around, right? Then divide everything by 10 and swap everything back. Then I repeat this entire thing. So as you can see, I just keep dividing and adding, and dividing and adding. And at the end of the day, we're gonna have here a 0 and then b as a final result. We're gonna swap this thing around and then drop it. And then in here, we're gonna do to dupe, which we're gonna compare with each other. Right, which we're gonna compare with each other. And if they're equal, that means they are palindromes. Then I duplicate b and I print b, and at the end here I just do to drop, which is totally fine. Okay, so this is a valid procedure. So this entire thing is going to essentially print all of the palindromes, right? So it's going to print all of the palindromes. Let's see how it's going to perform. Hopefully, so there we go. Okay, so look at that. It actually, yeah, these are palindromes. Yeah. But what's the largest one? What's the largest one? Interestingly enough, what if we are iterating this entire stuff? Starting not from 10 to 100, but actually from 100 to 10, and if we find the well, it may not work actually. Yeah, it may not work. So we need some sort of a way to have an accumulator. All right. So yeah, let's have an accumulator. Macro, and this one is going to be answer, and we're going to put it into the memory. There we go. So if this thing is what we think it is, right? So after the dupe, we have the value that we need to store into the answer. This one is rather interesting. B. So this is A and B. We're not going to duplicate anything yet. Duplicate B, then I put the pointer to the answer, right? I put the pointer to the answer, and then I load 64, dereferencing the answer. And if answer is less than B, actually something like this. If B is greater than answer, right? Something like this. We have to store B in there. Oh my god. We have to store it in there, right? All right, so essentially I'm gonna put answer, that is gonna be like this, and then I need to swap this entire thing, right? I'm swapping it. Fuck, maybe I need to duplicate it. So let's do dupe, it's gonna be B, answer. Oh, well, I mean, you can do dupe answer or answer over. It's gonna end up with the same shit anyway. Right, if you do answer, you're gonna do like this, and then you do over, you're gonna have like this, and then you can just store 64, and that will just store it in the answer. Answer over store 64 is actually looks pretty cool. I really like how it looks like. All right, and then after that, you do to drop. Okay, so that's pretty cool. And then we can do answer load 64 and just print this entire thing. Right, so we're trying to find the biggest palindrome. We're trying to find the biggest palindrome. Okay, so let me see. Okay, so we found it. 9009, there we go, it is 9009, but we have to do that for 3-digit numbers now, right? So it works fine for 2-digit numbers, and it actually finds what we want to find, but now we need to do that for 3-digit numbers. Are you guys ready? Are you guys ready? So now we need to iterate from 100 to 1000, right? So because this is going to be all of the 3-digit numbers. There we go. Okay, it is 906609. It is palindrome, but is it the biggest one? Let's find out. I mean, we can Google up the answers online, so probably. Keg W indeed. Keg W indeed. Okay. So is offline for maintenance. Oh, it's complete. For fuck's sake. Okay, so I know a pretty cool thing. Project Euler, Euler offline. So some time ago I actually found a pretty cool repo. Essentially, it's all of the Project Euler problems in a TXT file. But you know what's cool? They also contain answers. But they contain answers hashed with MD5. Well, it's actually a pretty bad idea to hash it with MD5, but it's just for your own discipline, right? So essentially, you have to hash your answer with MD5 and compare it with this one. But I'm pretty sure, yeah. So let's actually see. If I take this entire thing, right, and echo minus n, because I'm pretty sure they're hashed without the new line 906609, and it's going to be MD5, right? So this is the hash, and there we go. So this is the problem 4. This is the correct answer, right? This is the correct answer. So maybe we're going to use this instead of the Project Euler website, because this thing is reliable. Furthermore, I can just download this entire thing on my machine. right? And I won't care anymore whether the project order is online or not, right? So as long as my computer is online, it is going to work, right? So just gonna have it locally, and here we go. So that's pretty convenient. So I'm gonna give the link to this repo in the chat for whoever is interested, and I'm also gonna put it in the description for people who's watching on YouTube. Project Euler offline. So it's actually a pretty cool idea, right? Just have like a file, right? And I even started. So I think it's pretty cool. I think it's pretty cool. But here is an interesting question: can I actually brute force this, you know, hash? MD5 rainbow table offline. Right, so crack station. All right, so I just want to double check that none of these motherflippers leak my IP, right? So I'm gonna just take that MD5, right, another robot, check hashes. All right. Okay, I hope nothing actually leaks my IP. Just a second. All right, so yeah, you essentially can use the things like crack station or something like that to actually crack the answers. And as you can see, it's so using MD5 was actually kind of bad idea. Yeah. It is what it is. But I mean, it's like if you want to ruin yourself the pleasure of discovering the solutions, you just go ahead and crack it instead. But it's just like, I don't know. It is what it is, and it isn't what it isn't. All right, so let's go. Let's see if the solution that we wrote even fast enough for simulation. I'm just curious if the simulation. Okay, so this is how much time it takes for the simulation to solve this problem. So, you know, I'm starting to think that simulation mode in Porth is kind of useless. So maybe I should remove it. So first of all, it's not even that fast to be useful in the first place. And second of all, if I remove it, I'll have to implement less when we're gonna go self-hosted. You know what I'm talking about? Right, so yeah. So I'm actually like genuinely thinking to get rid of the simulation mode. So this is straight up useless. Like, I mean, how much time it should take? But maybe if we implemented the load 64 and store 64 intrinsic, maybe it would be, yeah. I think it was useful in early stages. Yeah, it is true. It is true. It was useful in early stages, but now the more we implement different features, low-level features, the more it becomes kind of useless. And it doesn't even support all of the syscalls. It only supports like a write syscall, and exit syscall, I think. Yeah, I think at some point I'm gonna just straight up remove simulation mode and I'm only gonna leave the compilation one. Yeah. So it is what it is. And it isn't what it isn't. Okay, so maybe we should solve another problem. What do you guys think? Problem 5. Oh boy. 2520 is the smallest number that can be divided by each of the numbers from 100 for 1 to 10 without any remainder. With the smallest positive number, what is evenly divisible by all of the numbers from 1 to 20? So I think I do understand how to solve this one. So we have to maintain the table. Yeah, we have to maintain the table of divisors. All right. So if we get a number, right? So let's actually go ahead and try to solve something. Euler. LCM. Well, here's an interesting thing. It might not be as easy as LCM, but maybe it could be implemented with LCM. I remember implementing it slightly differently. I remember implementing it slightly differently, but we'll see. Porth. Include std porth. So let's actually keep track of the current n. So the solution for n equal 10 is 2520, and we have to find the solution for n equal 20. So, but for now, I'm going to keep the n equal to 10, right? So what I want to end up with is the solution where I can just change the n to something else, and it's going to be a new complete solution. So now we need to iterate. So I'm going to duplicate 10 and actually n less or equal, right? Duplicate print 1 plus, and there we go. And let's do a compilation 5. And do we have stuff in here? Looks like we do. So interesting enough, I don't think we need actually 1, right? Because everything is always divisible by 1, so it's kind of useless to have. So the next thing I remember doing is I was trying to factorize this entire stuff, right? So each individual number I would try to factorize, and that is actually a pretty cool idea. And as I factorize, I store the values into the table. All right, so we already did factorization in a previous problem, I suppose. Was it for fourth one? No, it's actually the third one. Yeah, so here I'm doing something like this, duplicate, and I'm starting factorization, right, while over 1. So I'm still in factorization algorithm from the previous problem, so that's what I'm literally doing. And this is going to be the end. And in here, I essentially can do 2dup mod 0 equal swap over swap. Otherwise, 1 plus and there we go. So this is that stuff. So I think I'm already tired, but I want to finish this problem. I still want to finish this problem. So duplicate over 1, and then I do the division. So this is the x and the factor. And I just keep using it. And essentially what I want you to do is to duplicate the f, right? So I'm duplicating the f, then I'm gonna print something like this, right? Std out, right? And then print, right? And also here I'm gonna do print. Right, so what I want to do, I want to just see number and then factorization indented a little bit, right? So this is what I'm trying to achieve in here. Let's see if it's gonna work. And it didn't work because I forgot something. I wonder what exactly I forgot. I forgot to drop whatever we have in here, I suppose. So I forgot to do 2drop. Let's see. There we go. So that's kind of dumb. All right. Dupe print dupe2 over 1 mod 0. So what I want you to have in here is just a number and its factorization, but it never actually kind of worked. Which is kind of strange, right? So let me go over this code yet again. So we have an index, right? So I'm duplicating this thing, and then I push 2, Right, then I push 2. And the reason why I want to duplicate is because I want to preserve that index in the future, right? So that means I can just simply ignore this entire stuff. Index 1, and it's greater than 1, right? It is greater than 1, so it should be fine. Then I duplicate these two things, then I do mod, and then I compare this mod to 0, right? So that's fine. Then I duplicate 2, right? I duplicate 2, then I print the space, right? I print the space and I print this entire thing. Then I swap this thing around, copy 2, divide index by 2, and I swap this entire thing back. Okay, that makes sense. If this entire stuff was not equal to, well, it's not divisible, right? I just do 1 plus and I just continue. And after that, well, yeah, I think I don't see any mistake in here. That's the problem. I don't see any mistake in here, but it still doesn't really work. It still doesn't really work. So if I just do something like this, it is fine. I don't know, man. Okay. So if I take a look at this stuff, this looks fine as well. So here we have something like this. Maybe I have to do just a single drop. So where did I make a mistake? Why does it do it like that? I literally don't see a mistake. Where is the mistake? Yeah, so it just stops in here. Oh yeah, I know what's the mistake. Yeah, I know what's the mistake. I completely forgot. I definitely need to implement the static type checking. Write returns the amount of characters that were written. That's all it does. Right, so, and since we're printing 2 characters in here, it prints 2. So after write, we have to do drop. We have to drop the result of write. And now it is printing everything. So 2 is 2, 3 is 3, 4 is 2, 2, 5 is 5, 5, 2, 3, and so on and so forth, you see? So finally I have this thing. All right. So and we need to have like a table in which we're going to store the factors themselves, right? So, and the question is how we're gonna allocate the memory for how we're gonna lay out the memory. So I suppose the answer is going to be located at the beginning of the memory, right? So this is going to be the answer, memory end, right? And the intermediate one is going to be after the answer. And what's the size of the answer? Well, each element of the answer is going to be 8 bytes because we can only read 8 bytes. And multiplied by n, so this is going to be n multiply 8 multiplied by n and plus the memory, right? So with macros, it is actually relatively easy to lay out the memory, to actually define the schema of the memory. So I say here's where the answer starts, this is where the temporary table starts, and so on and so forth. So it's actually kind of useful. So, and probably before we start doing anything, I want to fill temporary folder, the table, not folder, with zeros, right? So I want to actually fill it with zeros. The question is how am I going to be doing all of that? So 0 while duplicate n less do, and we have an index. We duplicate the index, we do the temporary thing, and we add them together, and that gives us the pointer, right? The pointer. We need to store the 0 into the pointer, so this is going to be 0 over, and I'm going to do store right? Store 64, then 1 plus, and then the end. So here we clean up the TMP table, right? So this is a clean up the TMP table. One more time, 0, 0 n, okay, 0 over 0, copy 0, TMP plus that. Ooh, the TMP I actually have to go. Yeah, I think I fucked it up. Alright, so here is an index, right? So here is an index, and I suppose I want to do TMP. That will give me TMP. Then I do over index plus, then over again. No, not over again. Then 0, 0, and then store 64, and there we go. Okay, so this is how we're gonna clean up the TMP table. There we go. So I think this is how it's gonna be done. Cool. And now the thing is, every time we encounter the divisor, right? Every time we encounter the divisor, we want to use it as an index within the table, and we want to increment the element within the table, which is rather interesting. Can we have a macro? Can we have a macro increment 64? Right. So it will accept the pointer, and it will increment the value inside of that pointer. I think it's actually a pretty cool idea. So essentially, I want to duplicate whatever we have in this pointer, right? And we're gonna load 64, right? Then I'm gonna do 1 plus, that adds plus 1 to this entire value. And then I'm gonna do store 64, and this is the entire macro, right? So that way I can do shit like TMP index plus increment 64 without worrying of loading, storing, and stuff like that. So this macro system is actually very fucking powerful. Look at that. Look at that shit. Yeah. So first we introduced the concept of load 64 and store 64, and over that concept we introduced inc 64, and all of that without even modifying the compiler. Here's the interesting thing. I'm streaming for almost 2 hours and I'm solving 5th problem, and I haven't modified the compiler so far. So we haven't written a single line of Python code today. So that's what's cool about this entire stuff. What do you guys think? I think that's pretty cool, actually. I didn't expect, like, I was expecting to to dive into the compiler itself a lot while doing all of that, but I just don't have to. Even though things like load 64 and store 64 are kind of lame, I do agree with that, and we can improve them later, but I didn't have to go into the source code of the compiler. So, yeah. So the macro system is actually super simple, but it's super powerful. So yeah. Anyway, so what I wanna have in here. So at the top here we have a factor, right? And then what I can do with the factor is essentially use it as an index. So it's going to be TMP plus, right, increment 64. And that's it, believe it or not. So that's pretty cool. And after that, maybe I want to try to print the table. I think it could be a very good idea to try to print the table. Let's go ahead and do that. Oh shit, by the way, that's fine actually. Yeah, that's fine. So I'm gonna copy paste this entire stuff. Factorize, right? So factorize, print the table. So duplicate an TMP over, so here we have this thing, TMP over plus, and in here I might actually try to do something like load 64, right, just load 64 and just print this value after the factorization of our nation. But before I can do that, maybe I'm gonna actually do something like this, space, and then right, space and right, and also drop, and in here, dupe drop, dupe print. So that's pretty pogue, right? That's pretty pogue. So on each iteration, we clean up the table, we factorize the value, and we store everything within the table, and then we print the table. So all of that is not going to be part of the solution, but it's going to be just like to debug the solution. Right. So if I try to run and it failed miserably, which is kind of interesting. So it didn't even print anything reasonable at all. Okay, so what if I get rid of this entire thing? What if I get rid of this entire thing? So what do we have? It doesn't print anything. Okay, that's fine. All right, so... Oh yeah, I see. std out. I should have actually done std out. There we go. Okay, that's kind of cool. But this is lame. Oh, I forgot to drop, and yeah. So factorize everything, duplicate print, then I start from 0, std out write and drop, then tmp and over, then plus, then load this value and then print it, and then increment it yet again. So why does it print it like that? This is so weird. So it's almost like, yeah, it prints complete nonsense, if you know what I'm talking about. Why does it print complete? Is it because increment 64 is incorrect? One more time. Right, so if I have the TMP, right, I duplicate TMP, I load TMP, I do +1, and I store this entire thing back. Right, I store this entire thing back, so this is kind of strange. Okay. Yeah, so it only performs like a single iteration in here. This is the problem. It performs a single iteration, like what the fuck? And I don't understand why. Why does it perform only a single iteration? It's like... I'm really confused. Is that because of the 2 drop in here? But 2 drop in here is important. So, alright, so probably factorize actually fucks something over. Oh, I forgot the drop in here as well. Okay, so I see. I'm really glad that I'm using this language because I'm starting to understand what's needed to make this language more usable. Okay, so look at that. There is something completely incorrect with how we read and write, you know, values in here. There's something completely wrong. And you know what exactly? When we add the index in here, we actually have to offset by 8. Right, so we have to do 8 multiply. Right, so we're basically overriding the cells of the table. So, yeah, it's... Okay, so this is kind of... it's kind of interesting. And... Okay, so this is a duplicate, 8, Oh, and it has to be also the same. Yeah, I have to multiply by 8 everywhere. Right, I have to multiply by 8 everywhere. So this is over, but also 8 multiply, right? So 8 multiply, and also 8 multiply. There we go. So now, finally, holy fucking shit. Okay, so these kind of things, we don't have any static typing in here, right? So that kind of creates the problem. But each of these things corresponds to the amount of factors of the corresponding index, right? That's what we have in here. Oh boy. Okay. So, and right. I'm kind of thinking, I want to be able to print arbitrary table, not only TMP table. Maybe I could to like take this entire thing and put it into macro as well, if you know what I'm talking about, like print table. So something like TMP print table, and then at any point I could say answer print table. Right. So we can do something like that. I think it's actually a pretty cool idea. Just put this entire stuff behind the macro print table. And we know that the table has a size n, so we never have to worry about that. So this is going to be TMP. Okay. Dupe n. So this is TMP. This one may require actually changing stuff slightly, right? Because I do 0. Right. So then when I duplicate, I actually have to do dupe 0, and then we check everything. Okay, that's fine. Then we do that. And here we have TMP. Right. So here I can do 2 dupe. All right. So this is going to be 2 dupe. Then I need to multiply it by 8. Right, so this is going to be multiplied by 8. Then I sum it up. Right, so that will give me that. Right, then I load. Oh shit, it's not gonna work. Fuck. It's not going to work. It's not going to work. All right. Maybe fuck it. Maybe we don't need this macro, but it will be kind of cool to have this macro. But I'll have to rewrite this entire thing to accommodate for that macro. The thing that makes this code easy to write is because I don't have to store this pointer on the stack. Once I start storing this pointer on the stack, it becomes kind of difficult to work with. So that's why I don't think this macro is feasible. So I'm going to just remove it like this. Okay. So we are collecting the table, and now what I need to do is I need to add that table to the answer table. So I need to iterate answer and TMP table row by row, like element by element, right? And then store into the answer the maximum between them. Right. That's what I need to do. So let's go ahead and do that. So instead of printing the table, right, I'm going to be just iterating through the entire table. And answer, so this is the index. I'm duplicating the index. Duplicating the index and multiplying it by 8, and adding to the answer, right, and loading the value. So this is the value stored within the answer. Then I do over, right? So this is the index, this is the answer, right? Or rather answer index, like then I do over, multiply by 8, TMP plus load 64. Okay, so this is what we have on the stack. And if TMP is greater than the answer, we have to store the value of TMP in there. Right, we have to store it in there. So what we need to do, I need to push, I need to duplicate. So here is the address. Here is the address. Here is the address. And then I'm copying this entire thing over yet again. I'm loading 64, but after that I'm storing this back. Right, I'm storing this entire thing back. And that's it. I think this is how we're going to be doing that. Right. Yes. So we are merging the TMP table back into the answer table. Yeah, and after that we can try to print the answer table just to see how it goes. Right, we definitely need like a way to work with this kind of stuff in a more reliable manner. Okay, so after the entire solution, I just want to print the table. Right. I have a really weird reflex in here. Oh, by the way, I forgot to do a 1 plus. Drop 1 plus. So answer over. So this is index, answer, index, multiplied by 8, and add. So, and then I can do load 64 and get the value out of here. Right, I'm getting the value out of here. So then I do space, write, drop, actually std out, I have to do that on std out, and then I can do print. Right, I want to kind of sort of indent it to indicate that I'm working with the table. Okay, so, and there we go. So this is the final table. And what we have to do with the final table, this is a very interesting question. What we have to do with the final table, we have to iterate over it and essentially multiply all of these factors. We have to multiply all of these factors. So let's actually quickly do that. So we're already doing all of this, right? But we have to check if this thing is greater than 0, right? So if it's greater than 0, only then we have to add it to the final result. So, okay, so we have TMP and answer tables, but we need to put like this stuff into accumulator, right? So we need to have some sort of accumulator which will hold the answer. So we already have the word answer. So maybe I should rename answer to accumulator. Answer to accumulator. Let's actually do it like that. So this is going to be accumulator. And the answer, I suppose, right, is going to be TMP 8n plus. Right, so it's going to be something after the TMP. So first we have the accumulator table, right? So this is the accumulator, then TMP table, right? And then the answer number, right? So this is basically the memory layout. Yeah, so this is the accumulator, TMP, and the answer. That makes sense. So with the macros, we can just sort of like divide the memory however we want and then use these values. All right, so since it's going to be like factors and whatnot, I think we'll have to initialize this entire stuff. So this is the answer, and that store 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 64, right? So this is store 64. So we go into the accumulator, right? We go into the accumulator, we check that it's greater than 0, and essentially what we need to do, right? So we have an index, right? Here's the index. We need to, oh boy, since those things are factors, right? Since those things are factors, we have to repeatedly multiply this stuff by them. All right, so this is what we have to do. Okay, so this is the index, and so essentially this is the factor, right? This is the factor, and this is the times, right? So I take accumulator over 8, blah blah blah, and load 64, and this is the times. And maybe what I want to do in here is, while duplicate times is greater than 0, we're gonna keep doing this entire stuff, and every time we're gonna subtract 1 from the times. Right, so, and essentially what we have to do, we have to multiply the answer by the factor. So I have to do over, that gives me the factor. Then I take the answer, right? Okay, here is the answer, and I load the answer like this. Then I suppose I want to multiply this kind of stuff, so this is what I have now. Then I suppose I want to put the answer yet again in here, and I need to swap it, so to put answer here, and then I need to store this entire stuff back into the memory and end up with times, and then I'm going to do 1 minus 1, and it's going to be repeated until the entire thing is 0, and after that I can just drop these times, and I'm going to end up with a factor which is kept incremented. Actually, yeah, it's not going to be a factor per se, it has to be 2-dupe, I think. Is it going to be 2-dupe? I'm not sure. But the index is the factor. Yeah, okay. So that makes sense. Alright, so that has to be the thing. And after that I can just take the answer, I can load 64, and I can print this entire thing. Hopefully that's the solution, theoretically. Theoretically that's the solution. So yeah, I checked that this thing works correctly, so the only thing that may work incorrectly is this one. Hopefully it will work correctly. So let's go ahead and just do that. And 2520, right? So the final result is 2520. Wait a second. I think this is correct. Yes! Holy fucking shit, it works! Yes! It works from 1 to... So the only thing that is left right now to do is to switch n from 10 to 20. And we're done, pretty much. So, yep. Let's go ahead and do that. That's kind of interesting. Alright. So this is the whatever it is. So let's do echo md5 sum. And okay, so maybe I want to do that slightly differently, so I can copy paste this entire hash. And wait, did I fuck it up? Yes, I have to do minus n, right? So because it has to be without the new line. Fuck yeah. Maybe there is a simpler solution for this problem. People say something about LCM. But to be fair, I don't really see how you can do this kind of stuff with LCM. I think you kind of need this kind of table, but I don't know. So that's pretty cool. Holy fucking shit. I only wish the compiler would do a little bit more checks on the operations, right? So things like inc64 could be also part of the standard library, so I think I'm gonna actually put it into the standard library because it's kind of useful. So yesu, kawaii freaking desu. How about that? We solved 5 Euler problems today, and yep, I think that's cool. I think that's pretty cool. So I guess I'm gonna call it a day for today, right? So I think 5 Euler problems was enough, and I know what's needed to be implemented for this language. So I gathered enough information. So yeah, I think it was interesting. All right, thanks everyone for watching. I really appreciate it. Thank you for all of the subscriptions, for all of the bits and stuff like that. And I see you all next time. If you're watching on YouTube, check out the description for all of the links. If you're watching on Twitch, check out the VODs channel. And yeah, I gotta go. Thanks everyone. Love you all.